I now call to order the Society's 2,413th meeting in the 149th year since its founding on March 13th, 1871. Good evening, everyone.
Good evening.
My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Ben Reed in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on PSW Science's YouTube channel. I will begin with a few announcements, followed by a reading of the minutes of the 2,412th meeting and the lecture by Daniel Innocente on space architecture for a moon village. We will then turn to this evening's lecture, followed by a question and answer period. When the Q&A is done, I will present a small thank you gift to our speaker, make a few closing announcements, thank those who make PSW possible, and adjourn the meeting to the social hour. First, please join me in thanking the sponsors of the 2019-2020 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a generous donor who has asked to remain anonymous. I am pleased to announce that the following new members have been elected to the Society. Adrian Manguca, Director of Commerce at NanoRocks, interested in bioengineering, astronomy, engineering space platforms for long-duration human spaceflight, and complex systems theory, who comes to PSW through PSW GC member and Special Projects Director Cameo Lance. And Michael Nelson, Adjunct Faculty Member at Georgetown University, and consultant to internet companies interested in emerging internet technologies, cloud computing, and technology and innovation policy, who comes to PSW through the PSW Facebook page, which I think is a first. And tonight's speaker, Ben Reed, whose background and interests will be clear to you in part from tonight's proceedings. Please join me in welcoming them to membership in the Society. There is a signed reprint of Volume 1 of the PSW Bulletin for all new members. Please see me after the lecture if you have not received your copy. That is, if you're a new member and you have not received your copy. And if you purchased the PSW ribbon, please see Cameo Lance over there at the ribbon chat table, and she will be able to give you your ribbon. Recording Secretary James Heelan will now read the minutes of the 2,412th meeting and the lecture by Daniel Innocente on space architecture for a moon village, delivered to the Society and guests here in the Powell Auditorium on September 20th, 2019. James.
On September 20th, 2019, in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the 2,412th meeting of the Society to order at 8:02 p.m. He announced the order of business, that the evening's lecture would be live streamed on the internet, and welcomed new members to the Society. The minutes of the previous meeting were then read and approved. President Milstein then introduced the speaker for the evening, Daniel Innocente, Senior Architectural Designer of Skidmore, Owings & Merrill, or SOM. His lecture was titled Space Architecture for a Moon Village, Designing for Space Habitation. Until the 20th century, architects needed to rely on scale models and drawings of proposed structures to represent their vision. But in recent decades, digital technology arising from the aerospace industry has revolutionized architectural methodology. Modern structures can now be precisely designed to respond to the environments in which they exist. SOM is collaborating with federal government partners to research new methods of constructing smaller structures. For example, working with the U.S. Army Corps of Engineers to research using polymers to 3D print entire structures, and using gantry systems with additive manufacturing to explore building with cement. SOM is now collaborating with the European Space Agency and the Massachusetts Institute of Technology to collaborate on a proposal for constructing a moon village. The team is considering the structural necessities of such a village, mission design scenarios, and human systems. Innocente said, the three criteria key for evaluating a site for optimal development are the terrain, presence of water, and the existence of resources. On the moon, there are two distinct types of terrain, the Maria and the highlands. The poles are primarily highlands, which offer an opportunity for near continuous sunlight collection and consistent communication with Earth. Water is a medium for both energy and for life support. The project team believes that coal traps on the moon's south pole contain small water ice deposits at high elevation. The moon's principal resources are inside the regolith, silicate and oxide minerals. Innocente said accessing those minerals would allow production of tension structures and composite structures to shield radiation. The project team has identified a flat lunar landing site and considered the SpaceX Falcon Heavy and Blue Origin New Glenn rockets for transporting equipment to the moon. The transport vehicle will impact how equipment and any prefabricated structures must be designed to pack efficiently. Because rigid grounding is necessary to support a multi-level structure, the project team determined it could not entirely rely upon inflatable structures. The habitat they have designed is a registered shell structure and modular systems that may be assembled in space. Future structures will be constructed in situ by subsequent mission teams. The project team calculates 4.3 cubic meters of space per human body are necessary for moon habitats. Spaces must also be designed to facilitate human health and bodily functions. For example, the 400 cubic meter habitat is designed to maximize perimeter space, encourage as much human movement as possible, and to allow sunlight. Innocente described the structural design of the habitat shell with continuous curvature to minimize bending. He then described the materials and configurations the project team has explored for connecting rigid and inflatable habitat components. Inside the habitat is a composite floor system that needs to be designed for deployment inside the inflated structure. The floor assembly has a thickness of approximately 400 millimeters and may be used for storage. And while titanium would be optimal, Innocente said it is cost prohibitive, so that the floor assembly will be aluminum. The project team has also considered integrating natural and artificial light, both to maintain circadian rhythms and to entertain occupants. The Moon Village plan must also be designed to expand. The initial mission will deliver mobility systems and establish proof of concept, and subsequent missions will land bigger equipment to allow landing and moving habitats. After 4 missions, habitats will be fully functional. The project team is now considering how to extract and process lunar resources and how to construct surface systems like power stations, landing berms, tunnels between structures, and dust dispersion systems. Innocente described the various construction techniques and challenges the project team is considering for building such structure. He acknowledges the interdisciplinary expertise necessary for the Moon Village to succeed. And he said the project team invites experts to share their expertise to refine the village's design. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:36 p.m., President Milstein adjourned the meeting to the social hour. Temperature, 23 degrees Celsius. Weather, clear. Attendance in the Powell Auditorium, 148. Viewing through the live stream on the PSW Science YouTube channel, 20. Respectfully submitted, James Hewlin, Recording Secretary.
Thank you, James. Do we have any comments, corrections on the minutes? Hearing none, I will entertain a motion from a member to accept the minutes as read. A second. All members in favor? All members opposed? The minutes are accepted as read and will be posted to the website in due course. So I'm tempted to say we're going to take a 5-minute break, see if I can figure out how to fix the, unless you want to proceed with a handheld. You go with a handheld, okay. In that case, we will now turn to tonight's lecture on Immortal Spacecraft, the rise of in-space servicing, assembly, and manufacturing. It's my pleasure to introduce tonight's speaker, Benjamin Reed. Ben currently serves as the Deputy Director of the Satellite Servicing Projects Division at NASA Goddard Spaceflight Center. He is responsible for developing NASA's satellite servicing capabilities and coordinating these activities within NASA and with other government agencies, aerospace manufacturers, satellite fleet owners and operators, insurers, and other interested parties. Previously, Ben was Chief Materials Engineer for the Hubble Space Telescope, served as a member of the On-Orbit Satellite Servicing Study, the NASA DARPA Manned GEO Servicing Study, Robotics, Telerobotics, and Autonomous Systems NASA Roadmap Team, and the NASA Space Debris Removal Study. He also served as Director of Civil Space Policy on the National Space Working Group, setting government space policy, and served as Deputy Chair of NASA's Active Debris Removal Study. Ben is an expert on space environmental effects on materials, and before joining NASA, he held a number of engineering positions in private industry. He earned a BS in chemistry from the Catholic University of America here in town. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Ben to the podium.
Thank you, Larry. Thank you, Larry, again. Now I got something in each hand. Wow, what's my dominant hand? All right, so thank you for that kind introduction. As Larry said, my educational background is in chemistry. I then pretended to be an engineer for 12 years, the last 3 Hubble servicing missions, serving as the lead materials engineer. I then moved in when we stopped servicing Hubble Space Telescope because of the retirement of the Space Shuttle fleet. Began working with robotic servicing of spacecraft, the 99%, not the 1%. I'll explain what that means. And then I took a short hiatus for 6 months to work in the White House, serving as the Civil Space Policy Director for the National Space Council. National Space Council, as you all are, I'm sure, aware, takes a whole-of-government approach to space activities. NASA, of course, being one of the federal government agencies that is a prime stakeholder in national space affairs. There are many, many others. There are 24 members of the National Space Council. I was on the staff, not the Space Council itself. So, servicing, assembly, and manufacturing, I think how apropos that the previous speaker talked about in situ assembly and manufacturing of structures on the surface of the moon. That is part of my talk here. I'm glad he has set the stage for a good use case, the need for developing these technologies. Satellite assembly. You all may remember a particular individual named Wernher von Braun. Wernher von Braun drew sketches prior to the first satellite ever going into space of orbiting space stations that were to be assembled in space. So it is not a new concept, servicing and assembly. In fact, the first servicing mission, I would argue, took place in Skylab. Astronaut Ed Hoot Gibson, which I had the pleasure of meeting 2 weeks after joining NASA in 1998, on an EVA, a spacewalk, to repair the thermal shield which was damaged during the launch of Skylab. So servicing is not new. Assembly is not new. The desire or the need for in-space manufacturing, also not a new concept. So why am I here talking before you today? It's because recent investments that you as taxpayers have made in your space agency are coming to fruition. And now we can conceive of and engineer architectures and conceive of satellite servicing missions without the need for costly, expensive human involvement in orbit. We will still have humans involved on the ground, is coming to reality. So that's what I'm here to talk about. So we all know the reason why we go into space. There's many unique vantage points, right? Whether we need to get above the atmosphere to conduct UV science. I often get asked the question, why do we need Hubble at all? Let's just build big ground observatories. And there are quite a few big ground observatories. They serve a fabulous function in the ecosystem of astrophysics, of space astronomy. But the fundamental limitation is the Earth's atmosphere, of course. It is not static. And that water vapor produces the absorption in the UV that is impossible to overcome without getting above it. Just physically getting closer to things, right? We see this fabulous image of Pluto in the bottom center. It did not look like that when we viewed it from Hubble and other space observatories. It wasn't until we got New Horizons on top of it that we were able to resolve the incredible features that were never imagined before sending something out there. Asteroids is another thing. The Japanese have had several successful missions to various asteroids. Of course, NASA has now got a spacecraft, OSIRIS-REx, that is in very close proximity to Bennu. It turns out that Bennu is spitting rocks at OSIRIS-REx. It's spitting them out in general. We just happen to be close by, not because we're there. And in a few months, OSIRIS-REx is going to conduct its rendezvous. It's going to drop down, allow the gravity of asteroid Bennu to pull it in. The tag arm is going to make a single touchdown, collect sample, and bring that sample back to Earth. A little hard to do that staying here on the ground. So there are unique vantage points, unique opportunities that space affords. Some of those being exploration. As you have heard, United States, led by NASA, is executing a return to the moon. This time we are going to do it differently in several very important areas. We are going sustainably. We are going with commercial and international partners. Not the case back with the Apollo program. Sustainably with commercial and international partners. And oh, by the way, when we go back to the moon, we are going to bring female astronauts to set foot on the surface, another first. So, some of the technologies and capabilities that I will be describing to you today directly tied to especially the sustainability aspect for the new directive to go to the moon. Of course, the rovers on the surface of Mars have been there for many years. They continue to unlock the secrets of that planet. We have quite literally and figuratively just scratched the surface of Mars. InSight is there now, right? That is going to measure the temperature, the thermal conduction, the seismic activity, if they can get that mole to penetrate a little bit further down into the surface of Mars. I will be talking more about, sorry for jumping the order, the floating gateway that is going to be in near rectilinear halo orbit around the moon, from which sorties to the surface will embark. And then, of course, our favorite astronomical observatory, the Hubble Space Telescope, how the lessons learned and the technology developed with that observatory play into NASA's future plans. Commercial opportunities. So commercial companies have been making money in space. since the middle of the 60s. Telstar, Relay, right? That was the beginning of commercial endeavors in space. Geosynchronous communication satellites for a few decades was really the only venture that was commercially viable in space. Now today, commercial imaging, Planet Labs, DOI has started to bridge into a new area of commercial venture, one-day tourism. See that gorgeous photo of that spacecraft observation room that's going to go into suborbital space. I had the opportunity to lay down on one of those chairs. It was pretty neat. Unfortunately, they didn't let me take a selfie there. So, commercial opportunities, and the advantages that this brings to the aerospace community, and especially NASA, is that now when we want to do, well, nothing in space is routine. But when we wish to have more routine and less unique services in space, NASA has, and other civilian agencies and DoD and intelligence community agencies have the opportunity to compete for, to have commercial industry compete for services for that. National security. So the three main areas for space activities, as I've gone through them, is civil, commercial, and national security. Of course, everyone here recognizes the image on the right, that image of the exquisite resolution capability of the U.S. national security assets to, quite frankly, keep an eye on world activities. Space offers a unique vantage point. There's reasons to go there. There are a lot of high dollar assets, so I'm led to believe that the U.S. government has in space. So those are all the reasons to go. Now here's the part of the talk where I talk about all the reasons why it's doggone hard to be there. Space is a harsh environment. Let's just talk vacuum for 30 seconds. I seldom get to buy a new car, being a civil servant, but occasionally, once every decade or two, I'm able to afford a new car. And guess what? A couple months after buying it, you have to wash the inside of the windshield. Why is that? The low molecular weight polymers in the plastics in the car are evolving, and they're condensing on cold surfaces, like the windshield. Pretty soon, you get enough molecular buildup that it obscures the transmission of light through your windshield before those photons hit your detectors. And so you have to wash it because there's obscuration of the transmission of light. Space is no different. We build incredibly expensive optical components to go into space. There's plastic in those satellites. Guess what happens in vacuum? A lot more low molecular weight polymers are evolving out, landing on cold surfaces like mirrors, and now we have spent tens, hundreds of millions, billions of dollars on satellites. You get them into space, and they cannot take a clear image of the astronomical or the Earth or the planetary target that they're looking at because of this. So we spend a tremendous amount of money. I think the estimate for Hubble Space Telescope was 10% of its budget was spent on contamination control. 10% of its budget was spent on contamination control. Are there other industries on the ground that spend that much of their budget on contamination control? Well, in space, we do it because there's no way to get up there and clean the mirror. You got to do it right the first time. It's all in the preventive measures. There's no correcting it afterwards because it's in space. We humans are not there. Solar radiation, of course, you don't have the attenuating effects of the Earth's magnetosphere. If you're beyond it, of course, some satellites are inside of that. The orbital debris population, while this is an accurate representation of the tracked objects in space, each one has been blown up relative to what it actually is in space. But suffice it to say that the orbital debris population is only getting worse. Satellites are spending more time on building it to be resilient to impacts. They're spending more effort on collision avoidance. We, the US government, have spent a tremendous amount of money on radar and optical systems to track what's up there, so we can do a collision avoidance maneuvers when the things are trackable. If they're below an inch, they are not trackable, and we hope that they don't collide with our exquisite spacecraft. Space is big. I don't know if I'm the first person to announce that to the PSW, but if no one has said it before me, may I be the first? Let me find the camera. Space is big. Bigger than big. It is tremendously big. And to stay in space, of course, you don't just need to get that suborbital velocity to get off the Earth's gravity. You have to get into space and then head east or over the poles, whichever direction you're going, with enough velocity that the Earth gravity doesn't pull you back in. So it's really large, and you have to go really, 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 really fast to stay up there. Why does that matter for this talk? Because if you want to ever be visited by any other craft for a servicing, assembly, or manufacturing to benefit your mission, they too have to get to where you are and to match your rates. So people often say, oh great, space station is up there. That can be a great fueling depot. Everything goes there, they get gassed up, and then they go back to work. Well, it's like saying, I live in 4 miles north of Annapolis, very close to the Magothy River. Theoretically, I could jump in, half-mile walk from my house, jump in, and swim to London, and hop out and get a ride on that Ferris wheel. It's the same body of water. So yes, everything in space could go to space station to get refueled, but it's equally impractical to consider that because of the distances and the velocities needed to stay there. That gravity thing. It is very expensive to get off the Earth because of the gravity well. It's very expensive to get off the moon, only 1/6 as much because of the gravity there. Why have we not sent more things to Mars? Why has there never been a Mars sample return mission? Because of its gravity. To get things back off these gravity wells is tremendously difficult and expensive. So, you add all that up, everything we put there is crazy costly. And as a result of the orbital mechanics that I just described, it's very inaccessible. So why hasn't servicing, repair, refueling, assembly been more prevalent? Because it's costly and inaccessible to get to each other. There are a few notable exceptions. There are a few notable exceptions to this, and I will describe why those notable exceptions are notable exceptions and not the norm, but it is the rise of technology in the area of servicing, assembly, and manufacturing that I am here to argue will not make them notable exceptions into the future. So first, we're going to talk about the most mature of those three capability sets is servicing. The image you see here is a 2.2 meter arm, about yay big. It's a 7 degree of freedom arm, very much like the things attached to your torsos, and you all in YouTube land, your torsos too. 7 degrees of freedom. Shoulder, 3 degrees of freedom. You got the uppercut, the chicken dance, and ping pong, 3 degrees of freedom in your shoulders that are all independent of each other. 2 at the elbow, and 2 in the wrist. So why does that matter? Why do we care? Why am I bringing it up? Is because in a servicing mission, we don't know exactly what actions the robotic arm is going to have to take, as opposed to a robotic arm in a car factory where it is picking up the windshield and putting it on the new car. It's very deliberate action. That's all it needs to do. It can be lower number of degrees of freedom to do it. But we have evolved with 7 degrees of freedom because it allows us to do things like hold our manipulator stationary and move the elbow. Not very exciting, but that requires all 7 degrees of freedom to do that. We want the kinematic flexibility when we send robotics into space to handle the unforeseen situation. So, the proof of concept. Hubble is the ultimate proof of concept that servicing is worthwhile. 5 times. We risked astronauts' lives to go to the Hubble Space Telescope to improve it, to make it better. Wasn't just maintenance, it was to make it better. On 4 of those 5 missions, we installed new scientific instruments. Each instrument generation had a discovery potential 10x of the generation before it. So Hubble is 10,000 times more powerful today than it was the day it launched because it was constantly upgraded. And because of that, Hubble is the single most scientifically productive apparatus humanity has built. In the history of the human race, there is no apparatus that has produced more PhDs, more peer-reviewed articles, more inches of newspaper, front page, in the history of the human race, because servicing was able to correct the mistakes and upgrade the instruments. So it is that benefit that we wish to see applied to other assets as we move forward. Of course, you all have seen these images of Costars. So this is what the galaxy looked like before and after the corrective optics were installed in orbit. So that is a great example of unplanned repair. That was not planned before it launched, of course. And then planned upgrade allowed us to take a image of the very popular Eagle Nebula with the WIFPIC 2 camera, and with a subsequent generation of the Wide Field Camera 3, take an image of the exact same Eagle Nebula in the infrared as opposed to the visible. Proof of concept that servicing is beneficial. Nothing captures the emotions of the global citizenry than the images from Hubble Space Telescope because of servicing. So what investments have we made? Did we sit back on our laurels after the Hubble Space Telescope victories? Well, we had developed a cadre of individuals who had expertise in these areas, but rather than focus on Hubble, which was designed to be serviced, but since the dawn of time, there have been 8,000 or 9,000 satellites launched into space. Only a very few were designed to be rendezvoused or serviced. Of course, Gemini had 2 capsules come together. Apollo, service module, command module, lunar module, were designed to cooperatively mate together. Mir was designed to be visited. Space Station was designed to be visited, as was Hubble. But other than those 5 programs, none of the 8, and then there was Orbital Express, one other mission was designed to have 2 vehicles come together in space. All cooperative, all done with human in the loop. 8,000 or 9,000 satellites have launched. So what we did was, we said, why is it no other satellite has been able to be serviceable? Because they're costly, they're far apart. And since no satellite was ever designed to be serviced, nobody ever built a servicer because there were no clients. And so you had this chicken and egg, this vicious cycle. So we specifically set about a technology development program to develop capabilities to go to a satellite which was not designed to be serviced. They are harder to rendezvous with. They are harder to grapple. They are harder to unscrew caps or pull things in and out, whatever the task is, because they weren't designed to be serviced. So that's the technology challenge that was before us beginning of this decade. So what have we done? The first task in a servicing mission is get close to your client. That involves rendezvous. Without a human on board to look out of the windshield, or I think on the space shuttle they looked out the back window, not the windshield, you need sensors, you need cameras to be able to image your client to effect a safe rendezvous. So we flew to Space Station, a box, this exact box right here. This is testing on the ground before it went into orbit. Out here on the front face, you see the openings for visible, infrared, and LiDAR. There's visible, there's infrared, there's the LiDAR, sense and return, and a 2-axis gimbal right here. And so what this does on Space Station, you see the image here of the SpaceX Dragon capsule. This autonomously tracks it. in the visible, the infrared, and flash LiDAR simultaneously, it produces a 6 degree of freedom solution for where that craft is in space with onboard computation, nothing to the ground. It produces a navigation solution based on those 3 wavelengths independent of each other, combined together into a single nav solution to track the visiting vehicles going to space station. The harsh orbital lighting, the Earth moving below to complicate the algorithm finding the client. We wanted to prove in orbit that a craft without humans on board could autonomously track another space object. So we flew this to space station. It is up there right now. It's working well. We also flew to space station to practice or to develop our servicing capabilities. 3 experiments. The first one was called Robotic Refueling Mission 1. And creatively, we named the next one Robotic Refueling Mission 2. And I'm going to give you one guess what the one that's up there right now is called. Where we would fly legacy satellite interfaces on a 1 meter cube box, like this one you see right here. And here are 3 robotic tools up at the front. And here's what that robotic tool looks like on the ground and what it looks like in orbit in operation. And with these robotic tools up on space station, we practiced things like cutting a piece of wire. Sounds kind of simple for a human to do on the ground. Try building a robot to do it on space on a client not designed to be serviced. A little bit more challenging. So we wanted to practice before doing it for real. This is an image of what it looked like flying our box to orbit in the back of a SpaceX launch vehicle. And as a side job, just as a parenthetical note, turns out space station was having some issues a few years ago with coolant leaking, right? Every electronic, whether it's the phone in my pocket, the desktop computer at home, in a car, or on space station, all electronics, because of joule heating of electrons passing through wires, produces heat. And that's why computers have fans. It's hard to have a fan in orbit, so they run coolant through the avionics on space station to dump the heat into space. Well, with 600 pounds of coolant and a mile of piping, and all that orbital debris up there and all the rotating joints, you can imagine it's quite ripe for the opportunity for coolant leakage. That's exactly what happened. So we were asked with our robotic tool expertise to build an external leak locator for a space station. And here you see it, what it looks like. It's a quadrupole mass spectrometer that we space ruggedized. It's about yay big. And here is an image of it out at the end of the robotic arm on space station. They use it like a Geiger counter. They raster back and forth to look for the signal coming where the ammonia leak is, so they can then send an astronaut out to fix it. So servicing technologies helping existing spacecraft. So we practice on space station to do a servicing mission for real, and here is that servicing mission. It's called the Restore-L servicing mission. It's going to have 4 phases. The first phase, as I mentioned on the previous chart, is a rendezvous. You have to get up close to your client. So we have built a rendezvous system based off of what we practiced on orbit with the Raven project to do autonomous rendezvous with our client, which is in space right now. So who is our client? There's only 2 satellites designed to be serviced in space. That ain't one of them. It is the Landsat 7 satellite, built by Goddard. It's operated by USGS. They have graciously agreed to be a companion agency in this. They have made their satellite available. So it has been in orbit for 20 years. So we will be going to it to refuel it. It wasn't designed to be serviced. It has no doorknobs like Hubble has. It has no reflectors like Hubble has. Nothing about it is cooperative. It's not uncooperative. It's not going to run away from us, but it is non-cooperative. Big distinction. Uncooperative versus non-cooperative. It is non-cooperative. So to rendezvous with it is difficult. To get a couple meters away, and why a couple meters? How long did I say the robotic arm was? 2.2 meters. So we don't want to grab it with our arm fully stretched out like this. I have no way to make my arm longer when I'm at this singularity of my elbow joint. But if I move my arm like this, now I have the ability to change where my hand is. So we're going to cock our arm about like this, put it into this pose, bring the two spacecraft together. Well, it won't do anything. It'll be passive. We will move the servicer close enough that a second autonomous system, two autonomous systems running in parallel, will reach out to effect an autonomous capture of Landsat 7. So let's just think about degrees of freedom for another quick minute here. To have a chaser spacecraft going after another vehicle in space, that's a 6 degree of freedom problem. The chaser spacecraft needs to have the right orientation in this dimension, in this dimension, and this dimension, 3 degrees of translational freedom, and then 3 degrees of rotational freedom, roll, pitch, and yaw. 3 plus 3 equals 6. I don't know if I'm the first guest here at PSW to say that equation, but 3 plus 3 equals 6. Now the autonomous capture part. We've got a 7 degree of freedom arm for that kinematic flexibility. We will not be commanding that arm from the ground. It is autonomous. It will look up at that spacecraft to reach out and grab it based off the machine vision algorithms we have programmed into it a year before launch. 6 plus 7, that's a 13 degree of freedom problem. So that is the challenge with a non-cooperative client bringing them together in space. So when people ask, why hasn't servicing exploded in previous generations of spacecraft? That's a lot of computational horsepower needed. That is not a simple task to do with on-orbit computational processors. Because the harsh space environment, remember that chart? That ionizing radiation disrupting microcomputers, microprocessors in orbit, you cannot fly the microprocessor that's in this phone to space right now. It would not work. The generation of computers that are state-of-the-art in space are usually 3 or 4 or 5 generations slower than what we have on the ground. And so one of the reasons why it hasn't taken off is for that very reason. Once the 2 autonomous portions are done, and we then breathe again in the App Center, over the next week and a half or so, we will telerobotic, control with hand controllers from the ground, cut through blankets, cut through wires, unscrew caps, and then take a fueling hose and provide, deliver to our client 100 kilograms of fuel. And I have a video to show you next of what that looks like. When the refueling is done, we will move our client to a new orbit to demonstrate tugging services. We will then, completely separate, forget Landsat 7. The next task on orbit will be the assembly of a 3-meter Ka reflector. Doesn't sound very sexy, but it'll be a world's first assembly of a reflector, a functional reflector in space. It's not an optical mirror. I will talk about large mirrors on my very last chart, but Ka band is a little bit easier than wavelength of light, so that's what we're going to start with. And what's particularly intriguing about this on-orbit assembly demonstration that we will be doing is industry, commercial industry, brought that problem to NASA and said, I have geocomsats in orbit. I want to make them bigger and better and increase the revenue stream for my US company, for the US economy. And the way I can compete better in the global market is if I have larger dishes in space. So NASA, with your technical expertise, please help me develop the technology for larger reflectors in space. NASA assessed this and said, you know what? We could use that technology as well. We want things way out at Mars. We need large reflectors too. This sounds like something we can partner with you. So our fourth objective there, our fourth task for this mission was brought to us from US industry, and we are a willing and happy partner with them to do this on-orbit assembly demonstration. You see also with number 4 there, in-space manufacturing. I don't have a good cartoon of it, but we will be using additive manufacturing, as you heard the previous speaker at PSW last week talk about, the need to do additive manufacturing on the surface of the moon. Well, additive manufacturing in space also makes sense. And so the idea is that we will produce a 10-meter structure poking off the side of this spacecraft to demonstrate that we can. We'll do metrology on it, we'll verify its stiffness, and then we'll cut it off. It's a technology demonstration. Walk, I was about to say walk, crawl, run, but that doesn't sound right. Crawl, walk, run. Thank you, sir. So that's what we're going to do with unspace manufacturing. So all 3, servicing, assembly, and manufacturing with this one mission. And oh, by the way, all the while this is going on, part of my job is to make sure that as we develop these technology, and by we I mean your civil space agency, part of our charter is to make sure that U.S. industry and other U.S. government agencies benefit from that. So I spend probably 30% of my time working with commercial companies and other agencies to make sure that they are benefiting from the technical progress that we are making at NASA. So here is what that restore mission looked like. Please let me apologize first. There are a few jumps in the video. It's not quite polished. If I worked for a private company, it would probably be more polished before I got up here, but you know, NASA's got to remain humble somehow. So the robot arm is going to pick up the gripper tool. This is a tool that's going to grab that client in space. So there you see that 7-degree of freedom arm that I've probably over-talked about. It's now in the capture pose. It's cocked like this. The the chaser satellite moves ever so gently closer. And by the way, let me remind you, these 2 craft are traveling 16,800 miles an hour. They look stationary in the video. They're traveling 16,800 miles an hour. Now the robotic arm autonomously reaches out to grab that ring. The 2 craft are then brought together, sped up quite a bit. Let me just say that. We park the client on top of 3 posts. And now quickly, we've picked up a blanket cutting tool. Why do we need a blanket cutting tool? Because the fuel valve is covered by a blanket. So we're going to buzz this blanket on 3 sides, generating a natural hinge on that 4th side that we're not cutting. And now I apologize for the video. Here's a little, we don't have an invisible tool. We just don't have it in CAD yet. So that's not magic. That's just a tool that hasn't been mocked up in CAD yet to reveal the fuel valve underneath. So now we're going to use our wire cutter tool to, guess what? Cut wire. That's right. Freeing that center valve. That's the one we're going to go after. There are 2 caps that have to be removed. One tool is going to come in and unscrew the outer cap. We put that away. We bring out another tool that's got, actually it's the same tool with a smaller adapter. Think socket wrench with different sockets to remove that. And now finally the refueling tool. You see this hose coming off of it. Tanker below, client above. The robotic arm is bringing the 2 together. This is you at the gas station, grabbing that nozzle, sticking it in the car. A little bit more complex in space. That's right. And oh, by the way, a fueling system for a satellite's under 250 psi pressure. Our cars, no pressure at all. Otherwise, it would jump out at us when we open it. Satellites in space, 250 psi. So there's about 8 world's firsts you just witnessed in this video. So this is the mission where we bring to operational status a suite of servicing capabilities. It is not a Landsat 7 rescue mission. Let the recording secretary note. It is not a Landsat 7 rescue mission. It is a mission to bring to operational status a suite of servicing capabilities. It is also a mission to establish global precedents. 2 satellites coming together, you can imagine a lot of bad things happening if you were a bad guy and you wanted to get next to another satellite. These are absolutely dual-use technologies, and we are extremely proud and honored to be the organization that will do it, this type of mission, for the first time, setting a global precedence how to do it safely. We intend to be on NASA TV. Not that we get many more viewers than this YouTube channel, but we intend to be on NASA TV announcing to the world, permission to approach. USGS says, permission granted. And now we're 100 meters away. Permission to get even closer, permission granted. So even though we have well choreographed this with them, we want the global standards to be very safe, very transparent missions, TCBMs. We want to set the standard. I think I pounded that enough. So it is with that intention that we wish to make satellites more accessible, because you have the technology to do a safe autonomous rendezvous, and more cost effective. I showed you a couple of geo birds here. There's a government bird on the left, that's GOES-R, and commercial communication satellites on the right. Imagine the rocket before it leaves Cape Canaveral. It's about 750,000 pounds, kilograms sitting on the launch pad. 1% of that is satellite. So to get into space, we're throwing away 99% of all that mass. 1% gets into space, the 1% you see on the image. Of that 1%, half of it is fuel. Half of it is dumb liquid fuel. The other half is the dry stuff, the solar rays, the transponders, the stuff we care about. Actually, we don't care about the solar rays. We only care about the transponders. The arrays are there just to bring power to the transponders. It's a communication satellite, or it's a weather satellite. So 1/2 of 1% is the stuff we care about. All the rest of that is waste because we don't know how to do it any more efficiently. So that's part of what our job is. If you can refuel something, extend the life of something, or fly it to orbit with less fuel and more cameras, and if it works great and the technology hasn't been superseded yet, we'll give it 3 more years of fuel. Give it 3 more years of fuel. What we do now is we project ourselves 15 or 18 or 20 years into the future. What are we going to want for 15 years? And that's what we then start designing and building, and as soon as we launch, that technology is static. Hubble wasn't static, and it became the greatest scientific apparatus in human history. That's what we're trying to bring to other assets. Assembly. Assembly is a complementary set of capabilities. Payload rockets are really skinny because they got to go through the atmosphere, and when they're skinny, you got to cram your stuff into a small space. A lot of cost of a satellite is the foldables, the deployables, because guess what? If it doesn't fold out properly, you're SOL. Am I allowed to say that here? So assembly gives you the flexibility that when you get into orbit, you can build your thing big. You don't have to spend all your money with the origami. So many ground demonstrations have taken place, and a notable on-orbit assembly demonstration out of the Space Shuttle payload bay here. But what have we done with it? Well, certainly Space Station was assembled. That's a little bit different, right? Those are big, gigantic modules in an unbelievably capable space shuttle that were clicked together, as opposed to these gossamer strut structures, which you can get incredible volumes in space for the mass you carry to orbit through on-orbit assembly. So this is an extremely beneficial, extremely complementary set of technologies that we are working closely with to bring to your space agency. So let's talk, you see a version of what an on-orbit space station might look like around the moon. Let's talk about the thing on the right. There's an area of astronomy. I'm looking at exoplanets. How many exoplanets have we seen? It's a trick question. Nobody shout out. We haven't actually seen any. We think we know there are a lot there. Thousands of exoplanets have been found, but not seen. Right? We see the star that they're orbiting around dim, and we see the star wobble a little bit, and from those two we can infer the size, the distance, and the temperature of those exoplanets. But we have not imaged an exoplanet yet, because guess what? The doggone star is so bright that they're orbiting. If there was a way to block out that bright star, we could see the dim planets going around it, right? Put your significant other next to your headlight walk 100 yards back and try to look at their face. It's a little bit difficult. But if you can black out that car's headlight, then you can see the dim reflected light off your significant other's face. So that's the problem we have here. But with the ability to assemble a large star shade, like you see in that image on the right, we have the ability to image an exoplanet. So that's an aspirational goal for astronomy that assembly can bring to that community. And I'm guessing I'm nearing my time. I see all the time I want. Hot dog. We're only a quarter of the way in, people. In-space manufacturing. I mentioned we're going to do manufacturing with additive manufacturing of a 10-meter structure off of the Restore spacecraft. Here's another mission that NASA is working with, a commercial company. Commercial company came to NASA and said, we want gigantic arrays in space, but we don't want to deploy a big long thing because then the deployable becomes so complex that it overshadows the whole mission. But if we could assemble a beam that's very narrow at the tip, at the far end, larger at the base, now we could get some optimization through geometry, but we need in-space manufacturing to achieve it. And so there's a mission called Archinaut. It will be just as I have described. This structure you see here holding the solar array out will be manufactured in space. Very cool mission, starting to take baby steps into in-space manufacturing. The talk you heard last week was about more ambitious missions to go to the moon and make these gigantic structures. Well, here's a nice intermediate step. You see this socket wrench here, this ratchet wrench here in the center. That was manufactured in space. On space station, they flew a big bucket of powder. There's probably a better technical term for that. And then they put it into additive manufacturing. And actually it wasn't powder, it was ribbon. They put it into additive manufacturing machine, and they produced this ratchet wrench in space. So now we have broken some of that dependence on the Earth. If we want to send humans further out into the solar system, we need to break that dependence on Earth supply. We get there and something breaks. We get there, we forgot to bring the right tool. We get there and we want to do something we hadn't dreamed of. The ability to manufacture off-planet is incredibly freeing for architecture development. I've got 4 kids. They're all about the right age, especially my 2 daughters. They might be on the surface of Mars one day. And to bring them home safely, we just might need to manufacture something, a repair device or some other device to bring them home. That's reason to invest in the technology today. Large structures. In situ resource utilization. Now we're going to take the regolith on the moon, or Martian regolith, mix it with some polymer powder, sinter it together, and now we can produce extremely large structures to protect astronauts from dust storms, from radiation, from the sun, on planet. So these are the aspirational goals. These are the far-range goals for in-space manufacturing. So the Immortal Spaceship. I guess at some point in the talk, I should mention the title of my talk. The Immortal Spaceship. Right? If you are going to, and NASA is planning on launching the Gateway to orbit the moon, from which sorties will take place down to the lunar surface and back, as that is replenished, as the modules are replaced, as the broken components are serviced, as they are upgraded, as computers get better, cameras get better, life support systems get better, you can have a spaceship which is continually upgraded, maintained, a lot like the ship of Theseus. That is the Immortal Spaceship. That is the goal that we are looking for. So, the very last chart. The ability to construct an extremely large observatory. James Webb is absolutely fantastic. 6.5 meters. You know what would be double fantastic? If we could quadruple that. So that is what we are looking for, is the ability to have an observatory large enough to search for signs of life in our universe. That is what keeps us going every day. Thank you for your attention.
So we do have time for some questions, and we have a procedure with questions where we have 2 people with mics running around the room. If one of my runners will get this mic, there's a pink one and a red one, and you'll be called on in order of color. So keep your hand up, somebody will bring you the mic, and when you get the mic and I call the color of the mic that you have, stand up, tell us your name and tell us if you're a member, and then ask a question. Comments and speeches are for after the question and answer and adjournment to the social hour. You will have your day on the soapbox, but this part is for questions. Al, with the pink phone.
Yeah, my name is Al Ehrlich. I am a member. And it seemed to me that a great deal of what this system has to do, all your systems need, is artificial intelligence. Because when they reach out to grab something, they have to have some sort of visual system, I think, too. So do you have the does our planet have the artificial intelligence now, or are you having to develop that concurrently with the rest of the technology?
Yeah, that's a good question. We absolutely try as best we are able to canvas what is available, so we have to develop as little as possible on taxpayer nickel. That being said, the advent of self-driving cars certainly has produced a state-of-the-art of knowledge for vision systems that can recognize what does a person look like. Let's apply the brakes when they're in front of the vehicle. But space environment being what it is, with the computational power that we are going to have there as opposed to what cars can have here, lighting being different, velocities being different, we are having to develop most of it. So part of your question was, does the artificial intelligence exist today that we can simply use it? Not really. And we hesitate using the word artificial intelligence. We certainly have autonomous systems that are designed to operate without human intervention, so that if we have a comm breakage with the ground, at the worst possible moment, the 2 vehicles won't collide. Beyond that, when we're cutting wires, cutting blankets, pulling out tools, if we have a comm outage, we'll wait for the comm system to come back. Autonomy is incredibly expensive. Autonomous software is a lot more expensive than scripted or telerobotic software. So when I hear people talk about, yeah, we're going to make everything autonomous, I say to myself, you're probably not funding a program right now. Because if you're actually funding one, you steer clear of it unless you absolutely must have it. So I hope that answered your question. Thank you.
Red microphone and the pink microphone.
Are you able to comment on the on-orbit manufacturing potential and on-Earth economic potential of things like ZBLAN and other efforts on the space station?
Yeah, that's a super question. So there is a commercial company that has a business plan to produce incredibly pure and pure is not the right word, incredibly defect-free fiber optics in the absence of gravity. So this company is, I don't know where they are, if they've actually flown, if it's up there, or if they're about to. I apologize for losing lock on that. But the idea is that is a commercial company that has a commercial application for being in zero gravity, for in-space manufacturing. They bring the product back to the Earth and they sell it to people who want really defect-free fiber optics. I think it is a fabulous plan. It is right in line with what we're doing. Their need is for the defect-free. Our need is to make things that we didn't fly with us. So the use cases are slightly different, but the fact that they're taking advantage of a zero-gravity environment for commercial purposes, yeah, we highly support.
We've got the pink microphone. If you have a question, keep your hand up a long time because the runners can't see you. So pink microphone.
Sure, hi. I'm Adrian Manjuka. I'm a member as of today. Thanks, Larry. So given that movement between orbits is very difficult, Restoral is, obviously a tech demonstration mission. Is NASA considering at this time the economic viability of restoration missions or servicing missions across multiple orbits, or are you looking at just a single orbit, given sort of, plane changes make that pretty impractical?
But by inserting the word plane changes, I know you know something about orbital mechanics. Yeah, that's a great question. You'll recall chart 6 where I said space was big. Everything's moving fast. It is extremely propellant intensive to change planes, mostly to change orbits. So the way we have been contemplating use cases for servicing, think of neighborhoods, right? There is a cleaning service for the Annapolis area, and they service a 10-mile radius, not a 100-mile radius, because now the cost of getting the time to get the cleaners 100 miles out and back starts to dwarf what they're going to make when they're there. Same thing in space. If the spacecraft stereo A and B, a pair of satellites that NASA built to study the sun, one's drifting that way, one's drifting that way, the Earth's orbit, they are really far apart from each other. It is inconceivable to think of a servicing mission to refuel both stereo A and B as an example of what we are not thinking of doing. We are not thinking about refueling CubeSats. Just build another one, right? They're very, very inexpensive. But for high dollar assets, or for assets that are in the same plane where the delta V or the propellant cost to get from one to the other is low, that's what makes sense. So the geosynchronous belt, fabulous business case. The A train, LEO Polar, there's 7 or 8 satellites that are all in the same plane in LEO Polar, all government owned, all neighborhood of $1 billion or $2 billion each. Hey, there's a use case. Astronauts, keeping them alive at the moon. There's a great case for servicing. CubeSats and stereo, not so much. So we do think a lot about what makes sense economically. We're the stewards of your taxpayer dollars. We want to really think things through like that. It's a great question.
Fred, then Kate.
Yes, good evening. Mike Hilden, I am a member. My question in regards the commercial companies' ability to make their products more able to be serviced, and what levels have you noticed over time that they have increased their servicing capabilities or ability to have serviced capabilities on the satellite?
Thank you, Mike. Thank you. Excellent question. Yeah, wouldn't it be wonderful? So this image you see here, that's a mock-up of the GOES 12 back end. That's the ring we intend, that's a mock-up of the ring we intend on grabbing in space. If you look at the blankets next to the ring, it's all crinkly and shiny. What the heck is our camera at the end of the robot arm going to be looking at as it autonomously reaches out to grab that ring? It kind of stinks. It's really difficult. If that satellite operator, or the satellite builder, which is us at NASA Goddard, so I'm looking at myself in the mirror, only had the foresight 20 years ago to fly a bumper sticker. A high contrast fiducial, about yay big, black and white, kind of like a QR code. You guys have seen that. And they stuck it next to the ring. Now when the camera goes up at the end of that robotic arm, oh my goodness gracious. Thank you, Vanessa. Ladies and gentlemen, Vanessa Lloyd, the communications lead for my division. Thank you, Vanessa. There are quite a few of these now in outer space. You stick them with the adhesive backing next to your launch vehicle interface ring, and now when a satellite is, a servicer is going to capture you as a client, it has something to key off of. Guess what? It doesn't weigh much. It's very low programmatic impact to install it. And that is exactly the approach, the strategic approach we take with all things cooperative servicing for clients, not the servicer side, the client side. Low programmatic impact. If we say to NOAA, to NASA, to the Human Spaceflight Program, to a commercial operator, hey, your satellite needs to weigh 10% more, and then it can be serviceable, they're going to kick me out of the room. If I say it needs to weigh a half a gram more, I say, hey, Ben, that's wonderful. Let's talk. And so we have found that the satellite cooperative features that we design, the lower programmatic impact they are for the satellite builder, the more they let us stay in the room and be part of the conversation. So we are having those. There are many government organizations that are very keen on adopting some of these. So we are definitely headed in that direction, but it would take me another hour to describe all the cooperative features that we are designing. I will spare you all that torture. Hey. Sir, oh, sorry.
I'm Bob Hershey. I'm a member. Could you tell us more about the new materials you're planning?
New materials. As a materials engineer, I thank you for that question. The trouble is, when I became a manager, they made me forget everything I ever learned about materials engineering. So the particular group that I am working in at Goddard as a space flight center, the F and GSFC, they're important there. Our mission is application focused. What can you fly? And that is what you see here. There are research centers, and I will highlight Langley Research Center down in Norfolk, Virginia. At that research center, they are the experts in new materials. Those struts that I showed you in the assembly page, all that is Langley's work. I tip my hat to them. They are by far the experts in on-orbit assembly of those struts. What should the struts be made out of? What should the connectors be made out of? That is their expertise. I will not embarrass myself trying to repeat the research, say out loud the research that they are doing, because I won't do a good job of doing it.
Carl, you don't have to stand up, Carl.
Hi, Carl Merrill. I'm a member. In the previous presentation on the Webb telescope,
Yes.
they pointed out that it would be out at the Lagrange point, which would be too far to be serviced. Has that changed? Will we be able to service it? And the second question I have is, what about a major solar event? Are any of these systems going to be able to survive that?
Wow. Well, that second one is a tough one. I don't know what major means in your sentence, but the sun is a dynamic celestial body. Yes, space weather is a critical a space environmental effect that we have to build our satellites to be able to withstand. Back to, they're all costly. That's a great reason why. Now the more difficult question, James Webb. I could talk for an hour on Webb, but I will try to reduce it to 1 minute. The primary design phase for James Webb Space Telescope took place about 15, 20 years ago. If I was as mature as I am today, 20 years ago, I don't know what conversation we'd be having now. I wasn't, so here we are today. They designed it, they built it, and then we became mature, and then I started throwing around little decals like this, and they said, that seems pretty reasonable, Ben. We'd be happy to fly a few. I'm condensing like 3 years of conversation into one sentence. So James Webb will not fly with nothing. Now, the function that this will serve will be Webb arrives, Webb rewrites textbooks for a decade. I believe that is the planned operational lifespan for the fuel supply inside Webb is roughly a decade. But we see with Hubble, Hubble is 29 years old and still growing strong, knock on wood. That is the intention for Webb as well. And so the idea here is that Webb is a candidate for cooperative refueling at the end of its fuel span, and that is why they have agreed to fly some capture decals next to their Marmon ring. Great question. Thank you.
So we'll do the pink, and then we'll do red and take some questions from the web.
So I'm the pink.
You're pink.
So first
Could you
of all,
stand and tell us your name and if you're a
my
member?
name is Frederica Darima, and I'm a member. So I appreciate very much the comment that you made in response to the question how much AI we're using, and you said that some of it is automation. And also, I would like to push more on that. You kind of characterize some of your examples that you use they're autonomic, and I would say they're automation, when you have an algorithm, I mean, for example, to, in a sense, let's recognize that ring, that is, it's a known satellite, so this whole structure is known. So there is more automation rather than autonomy. So what do you define as automation then?
So, to be a little bit more explicit about the type of autonomous systems, you are 100% correct. We will have an uploaded model, 3D model, inside the spacecraft. The first phase of the mission, which I didn't go into detail, will be a fly around. We'll fly around it for several weeks, and we will be using the on-orbit imagery to update our onboard model. We will then begin the rendezvous portion of it, and I didn't go into that detail, but the rendezvous portion is not purely autonomous, or maybe that's not the right word. We're going to use supervised autonomy. So supervised autonomy means we are telling you to go from 1 kilometer away to 100 meters away. You're going to do it autonomously. If you get an abort call from the ground, you need to execute, based on what state you're in, a series of maneuvers to get yourself into a safe position. So it is not fully autonomous, it is supervised autonomy on a known target. It would be different. So that is our approach. At every step, we're giving it a certain waypoint to head towards. If it doesn't hear from the ground, or if it gets an abort call from the ground, it will get itself out of Dodge. If we were going to an asteroid, like OSIRIS-REx is at Bennu right now, where we did not have a pre-launch model of that to upload, it's a different story. But what they did was, once they got close, they took imagery, and then they built a model, and then they swooped in. So you're right, it is stages of autonomous activity, not fully autonomous. Stages of automation, as you said, not fully autonomous.
So we'll go to the black microphone and questions from our web viewers.
We have a question from the web viewer who is not a member. He asks, is there any standards being developed to increase serviceability?
That's an excellent question. So we are not a regulatory agency. We are not a standard setting agency. That being said, I fully anticipate the techniques and the cooperative servicing elements that we are developing will become de facto standards. The decal, we have developed a cooperative fuel port. One of the hardest parts of this mission is cutting through the blankets, cutting through the wire, unscrewing caps, threading onto that valve. So because we are building hardware to access a legacy satellite, we know the hardest parts of the mission. It's where I'm spending the most money. And so I told those same engineers, if you were king and queens of the world, what would you want to be accessing? Let's design that. And so we did. So we have designed a cooperative fueling port. It is called the Cooperative Servicing Valve, or CSV. By the way, everything at NASA must be turned into an acronym, and we have obliged that requirement. So the CSV has been patented. It is available for commercial license. We are encouraging any and all satellite builders and manufacturers to put one on their satellite. If they're never serviced in orbit, that's okay. It's the same size and mass as a regular fuel valve. So we did not design it to be a standard, but I'm pretty sure it's going to turn into a de facto standard, because there's going to be some in the market, there's going to be some in orbit, and there's presently no other similar valve. So that's my standards answer. But I do agree with the overarching intent behind the question, and that is standards are good. It allows for interoperability. It allows for a commercial servicer, for example, to fly one refueling tool and be able to hit multiple clients because they all have the same size interface. It's an excellent question.
So the pink microphone, we'll take a few more after that. I think there's a black one somewhere. Got a question up here.
Is there a paradigm system or one of the best of several paradigm systems which is viewed as a test of this kind of sort of concept? Any particular sort of mission that is creating around, or is it just kind of taking on its course as it goes?
Let me see if I got the question right. So the question is there a driving need case, a particular design reference mission?
Yeah, 104.
Sure. So when we started thinking about how to bring to operational status this suite of servicing capabilities, we could have designed the first point design mission, the paradigm busting mission to go after a CubeSat, but it didn't really make sense since that's not what people will use it for in the future. We could have designed it to refuel a lunar lander. And while that is important, and we are helping NASA in that area, that's not really a broad general use case. And so we thought long and hard about what is a logical use case for these nascent technologies, and let's design that first mission to be that. So what did we choose? We chose Landsat 7, neighborhood of $1 billion, owned by the government, a high-value asset that is still doing incredible science for you, the taxpayer, for the world community, every minute of every day. That seems like a nice logical case, and it's next to the A train where there's a lot of other clients. And so we specifically chose that as our proof of concept for all those reasons. Great question.
We have the microphone over here, the black microphone.
Mark Briel, not a member yet. So there's an obvious cost trade-off, launching a new spacecraft to service the existing spacecraft versus launching a replacement of the existing spacecraft. Is there any longer range plans of maintaining a servicing vehicle on orbit to do repeated servicing missions as opposed to having to relaunch a new vehicle for each servicing mission?
Yeah, excellent question. I don't think NASA has those plans other than maybe to the lunar architecture. But commercial companies are absolutely thinking along those lines. There happens to be a startup that is developing its technology right now. It's called Orbit Fab. And Orbit Fab's business plan, and I'm going to probably misstate it, they would say it probably slightly differently, but essentially their business plan is gas station in space. They want to be a fuel hub where servicers can come, tank themselves up, and go hit some clients, come back to the Orbit Fab, and go do it. And so I'm going to guess they're going to put that in a logical orbit where there's a lot of potential clients and not off in left field somewhere. So absolutely, people are thinking those ways. NASA doesn't have any intention to do that because we want commercial industry to sell us those services on best value to the government. Is that the right phrase, Mike? And the best value to the government instead of having to do it ourselves. So part of NASA's job is do the hard stuff, do it once, do it first, turn it over to commercial. So that's our plan.
So last question, pink mic over there. Make it a good one.
All right, Gary Dudensky, not a member, but used to be a member. I'll sign up again. So MEV is going to launch in whatever next few weeks. Once so what does Restore L give more to the world than like? In other words, MEV is a commercial product, right, with similar capabilities, being able to service. And so on. So how does Restore L contribute beyond what MEV contributes?
Yeah, the devil's in the details, and so is salvation. Admiral Verkover quote. So MEV is a commercial spacecraft that is set to launch out of Baikonur the next couple of weeks, as you mentioned. Launch has been scheduled, but it has not been announced yet. MEV is a commercial product that's going to go to GEO, as I mentioned, with 450 satellites all in one orbit plane. It's a logical place for a business to send a servicer. It is going to rendezvous with and make a physical attachment to a legacy client. So up till now, the similarities to what Restore is doing is pretty tight. The Venn diagram has got a lot of overlap thus far. But that's where the similarity ends. Once the MEV is attached, the client satellite will turn off its attitude control system, and for the next year, 3 years, 15 years, whatever the life of the lease is, or the terms of the agreement are, the backpack satellite, the MEV, the jetpack, will be doing attitude control services. A geocom burns about 35 kilograms of fuel per year if it's a hypergolic system. And so 35 kilograms a year, that's why half the satellite mass is liquid when it launches. They do not need to expend that fuel if a backpack is doing it for them. So they are not refueling, they are not repairing, they do not have dexterous arms. None of this is a negative. They have a different business plan. They're a commercial company. We're NASA. We want to build observatories to look for life on another planet. That's the technology suite that I am building towards. Refueling is a step along the way. A commercial company has different objectives and different goals, and so the MEV is going to do life extension through attitude control services different than what Restore is doing. They are not also doing an assembly demonstration or an on-space manufacturing demonstration. Not better or worse, simply different.
Thank you, Ben.
Thank you, Larry.
Before you go, yeah, it's just tricky now with a microphone in my hand, but before you go, I'd like to present you with these tokens of appreciation for coming down here and sharing your time and giving this informative talk. One is a framed copy of the announcement of your talk, signed by all of the members of the General Committee on behalf of all of the membership. And the other is a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington. Yeah. And it has, among other interesting things, the description of who the founders were and why they founded it, and what they hope to achieve with the organization, and why they called it the Philosophical Society of Washington instead of the Science Society of Washington. But we call it PSW Science. So thank you very much. I'll take the microphone.
Thank you.
I think Lauren will escort you to the back of the room. And before we go, we have a few housekeeping announcements. PSW depends on members and sponsors, as well as our lecturers. If you're not a member, please note that the 2019-2020 dues notices have been sent, and if you have not yet paid your dues, please do so. And please consider making an additional donation, sponsoring a lecture or a lecture series. And gosh, volunteering to help carry out the Society's activities. If you're not a member, please consider joining. It's easy. You can apply via the website. You just go to the home page, look in the upper, I'll try and use the confidence monitor. That's a new thing. Yes, go to the upper right-hand corner and hit the join button, which will pull up this page, which has a link to a membership application, and when you fill it out and get to the bottom of the page, has a submit button. And when you submit, it'll bring up the payment page. And when you pay, we'll be very happy to make you a member. All that's required is, besides your payment, that you are interested in science. And don't expect to come and talk about Plato and Socrates during the regular meetings. We can do that afterwards at the social hour or even after that. You can make donations via the website as well. And you don't have to be a member to give us money. We accept donations from non-members as well. A PSW is a nonprofit educational organization tax exempt under Section 501c3 of the Internal Revenue Code. Contributions are tax deductible to the extent permitted by law and the IRS. And all PSW members in good standing may wear the PSW rosette. If you wish to purchase one, it's $15 plus tax, and you may do so at the rosette table, which is currently being attended to by Cameo Lance over on your left-hand side in the front of the auditorium. Our next lecture will be the 2414th meeting of the Society. And the speaker will be Neil Devaraj, who is a professor of chemistry and biochemistry. It's really one department, but the biochemistry people, the chemistry people don't get along very well, so they split the name. And the bioengineering department at the University of California, San Diego, and in beautiful La Jolla. And he will be talking about bottom-up synthesis of systems that behave, reproduce, and communicate like life. It should be very interesting, and Neil is a great guy. So I commend the lecture to you. It is sponsored by PSW member Jerry Harasowicz. The next lectures in the rest of the fall series, we have TESS's Exoplanets by George Ricker, who is the TESS principal investigator and director of the CCD lab at the MIT Kavli Institute for Astrophysics and Space Research. That lecture is sponsored by PSW member Bob Terry. Thank you, Bob. After that, we have a talk by Dean Romich, who is Distinguished Professor of Oceanography at the Scripps Institute of Oceanography at the University of California, San Diego, in La Jolla. And unlike the main campus of UCSD, the Scripps Institute is really on the beach. And he will be talking about Argo. In case you don't know what Argo is, Argo is a network of about 3,200 autonomous sensors that are floating in the oceans of the world that periodically submerge and go down to, I think it's about 1,000 feet. And then they slowly resurface. And on the way up, they take measurements of salinity and temperature and other ocean parameters, which they then report back via satellite to a big data center. And they're gathering the most complete set of data that we have on these parameters for the world's oceans. And it is sort of a harbinger of the sort of environmental sensing, autonomous flotillas and distributed systems that people are wanting to put together. And finally, we have, well, I guess we have more than that. On December 6th, we have Harold Hess, who's the group leader at the Howard Hughes Medical Institute at Genelia. This is sponsored by PSW Science member Tim Thomas. Thank you, Tim. And he'll be talking about the brain in super resolution 3D large volume molecular mapping of brain circuits. He worked with Eric Betzig, who won the Nobel Prize not too long ago for this sort of work. Oops. Boy, everything's off today. And we don't have a speaker yet for January 10th, but on January 24th, Ellen Stofan will be speaking on Venus, and she is the Adrian Mars Director of the Smithsonian's National Air and Space Museum. The schedule is complete through March and actually beyond that, and will be posted in the not distant future. For now, please note that the President's formal dinner and lecture that night will be on February 21st, and it will honor Joachim Frank of Columbia University, who is the inventor and developer of single particle cryo-electron microscopy, and the winner of the 2017 Nobel Prize in Chemistry for this work, along with Jacques Dubochet and Richard Henderson. Also worth noting is that on May 15th, we'll have Shep Dolman, who was the lead scientist on the Event Horizon Telescope Consortium that not long ago reported their historically significant first, a direct non-image of a non-black hole. No, I'm sorry. A direct indirect image of a black hole, because you can't see black holes. With that, let me thank our crew tonight. James Hewlin, who read the minutes. Robin Taylor is hiding way in the back there, who actually does pretty much everything. Does a live stream in the video director, Connor Nixon on actually camera number 2, and Noah Block on camera number 1. Sorry about that. Camille Lance, our room manager, who also handles chat and rosettes, Laurel Kane, our best girl, who's over there by the door, and our red, blue, and black mic runners, although sometimes it wasn't red, blue, and black. We'd also like to thank all the members of the General Committee, who I'm not going to read. And with that, we will entertain a motion to adjourn the 2,413th meeting of the Society to the social hour. Bob, do we have a second? A second. All members in favor? Aye. All members opposed? Well, I guess we're going to have to adjourn to the social hour.